This talk is about K8 Kubernetes operators for enabling hot restart of stateful applications. But I also want to talk more generally about the memory problems that the computer industry faces. So I'm also going to be talking a little bit about CXL technology. So all the stuff I'm going to be talking today is pretty much a preview of things that are about to happen in the industry or are proof of concepts that are very close to becoming realized. So here's the outline of my talk. I'm going to be, first of all, talking about this concept of transparent checkpointing and restarting, give an overview of that, and I'll talk about doing CPU-based checkpointing on Kubernetes, and then I'll pivot over to GPU checkpointing and restarting on Kubernetes, and then I'll go through a demo of this actually working. After that, yeah, hello? Or should I talk closer? Okay. Yeah, and then the next part of this presentation, I will talk about something called CXL technology, which stands for Computer Express Linked Technology. It's an extension of memory technology across PCIe buses that's been adopted by the entire industry. And I'll talk about use cases for CXL, both in Kubernetes and also for accelerating AI workloads. And that involves memory tiering, memory pooling, and memory sharing. So first of all, let me start with the first topic, the what and why of transparent checkpointing and restart. The what is that the idea is to capture and restore an application's running memory state, machine state, and coordinate with data storage and not have any application changes required. Hence, we call it transparent checkpointing. There are other kinds of checkpointing technologies where it's built into the application as domain-specific knowledge. Many AI, ML workflows, for example, know how to checkpoint during various parts of their pipelines and also during training epics. But this is transparent checkpointing, which requires no application changes and allows operators to do greater flexibility in managing their infrastructure. This checkpointing I'm going to be talking about also is not intended for what we call live migrations, but this is really for hot restart of applications. So it does have a fairly narrow recovery time objective associated with this kind of approach. And the why of this is that we want to provide fault tolerance for long-running applications and workflows that do not have built-in checkpointing and restart. In the Kubernetes community, for example, people are actually trying to start running HPC workloads, batch workloads on a Kubernetes infrastructure, or they're running a lot more AI workflows. Same thing. Some of these can take a while, and if they fail asynchronous to its built-in checkpointing, it could still be problematic for users. And another reason is that the platform and infrastructure operators, many would like to be able to rebalance and reprioritize workloads while minimizing disruptions. So for example, when you're auto-scaling, you may want to auto-scale and align GPU workloads better or have higher priority GPU workloads run ahead of other ones while not losing all the work that's already been done on the existing workloads. So there's a variety of reasons we see for having this kind of transparent checkpointing in those use cases. And another area is also for the ability to do branching, cloning, and preserving of workflows and pipelines. We've talked to people that want to save their, we've talked to SaaS providers that, for example, have Jupyter Notebook clouds, and people go home at the end of the day, or they just forget their machines, and then they come back and they're either reclaimed and everything's lost or whatever. This kind of technology could be used to automatically save all that stuff and shut down those instances and then bring them up the next morning. So that there are use cases like that that we see interesting for this technology. So this goes into some more examples of using transparent checkpointing and restarting. One is just to be able to have periodic snapshots in case there is a failure, a hardware failure, whatever. We can roll back in time to a specific checkpoint and resume operation without having to go all the way back to the beginning. The second one is for time travel, where there could be a multi-stage pipeline, and you can annotate in your pipeline that you want a checkpoint done at this junction of a pipeline. And for some reason, if you want to roll back to that stage and iterate and go a different direction, that's a possibility. We've seen people in the computational biology area where they're doing machine calibration. They will literally clone instances of our compute and then run them in parallel because they have enough cores available, so they can try different calibration settings and actually do a little bit of parallelization of their workflows in that fashion. And then I think another interesting one for Kubernetes is application migration. We have people that want to burst from on-prem into the cloud. They want to checkpoint that. They want to move it up to the cloud. They don't want to have to restart it from the beginning. They want it happening transparently to the users. They want to run spot instances where you can save 70, 80% on your spot instances. They want to migrate from smaller instances to larger instances, or back down to smaller instances because of running into problems or actually over allocated instances. Either way. And then last, clones for work group collaboration, like that example I just cited earlier about with Jupyter Notebooks. How do you automatically preserve all these notebooks, everything, even the machine state, everything, and bring them back the next morning, and nothing's lost, and people can be more productive in that fashion. So the basis of all this, I want to make sure you guys understand. This is we use Creo. Creo is an open source project that's been around since like 2012, so it's been out there quite a while. I believe it's used in Docker and Podman and Virtuoso's virtual VM migration, things like that. It's a relatively mature technology, and I'm providing the link to this to the main page of that open source project. So this is sort of a core piece of what we've developed at Memverge that I'll be demonstrating. And the way it works is that it does the checkpointing of the application at the process ID level, so it can go all the way down the tree and checkpoint all the child processes. And I'm not an expert on this, but the high level way this thing works is that it uses ptrace to freeze the process and execution, and then capture some of the machine state. The rest of the machine state has to be captured by this clever technique of injecting this parasite code into the application itself to drain things like file descriptors, signals, timers, and events, and then and bring those out. And what happens is it gets dumped into serialized and dumped into a file, and then once this is done, you can it either removes itself, this parasite code, and you can resume operation, or you can just kill the process. For example, if the node's being shut down or whatever, you can just kill the process. And the restore process is basically the reverse of this. You launch this master restore process, which recreates all the child processes, sorts out the shared resources. Some areas have shared memory, and then sets up a position-independent code mapping in each one, and then each child then goes about restoring its own state and morphing itself. So it morphs from Creo into the original processes, essentially, and gets it synchronized, and then eventually it unmaps Creo and resolves all the virtual address mappings. And then the master restore process kind of unhooks itself. It's almost like a reverse of the parasite, and allows the original process to resume execution. So this is a foundational piece of doing transparent checkpointing and restore. I think in the Kubernetes, it's in alpha mode, I believe, some variant of this for use for forensics on containers. But yes? Yeah, actually, I haven't seen ptrace be the performance problem. Actually, the performance problem has been more just the time it takes to transfer things around, empty files. And I'll just show you that in just. Yeah, we are. And I'm trying to minimize that freeze time, and I'll show you in a little diagram here in just a second how that works. So anyway, Creo itself, we consider it to be a good start, but there's other things that have to be considered to make this usable by a system admin or an operator. One is the snapshot overhead, how long it takes to actually freeze. It could take several seconds. So again, this is not a live migration. This is what we call a hot restart type of use case that we're pursuing. And so there's overhead in terms of time. Like, for example, we've tested this with some EDA workflows, half terabyte applications used for simulation of semiconductor designs. And I think the freeze time could be several seconds, right? So that's that order of magnitude. And then also there's an issue of the space consumed, right? So if you take a snapshot of this memory and you just double the size of the memory, well, you just double the size of the instance you might need, right? So that kind of problem. And then, so compute resources. So all these things have to be taken into consideration, the drain time. And so the way we've been addressing this is to make Creo more usable in these more production-like environments by doing what we call an asynchronous draining of the instance, and then also an incremental checkpointing. So right now, the default situation is you just snapshot the entire memory, and if the memory's half a terabyte, well, and you only can dump it at 3 gigabytes a second, you have a big problem. If you have a spot instance situation where you get 2 minutes basically to drain this thing. So we're trying to address those kinds of problems. And then also the storage space consumed, using hardware, using compression techniques to compact these files and remove duplications. And then the other trick to this is to integrate with external events such as, for example, in the AWS cloud, you have these spot instance preemption signals. What do you do? How do we integrate with that? Or the Kubernetes scheduler, or we've also had to work with resource managers like Slurm, LSF on the HPC side, and then cloud platforms. People have things like AWS Batch where they want to use this kind of technology or whatever. So security. So security is another aspect of this. And then a lot of times people, even in Kubernetes, are using temporary or ephemeral files on those instances, associated with those pods or nodes. And so those also need to be coordinated along with data storage if you want to capture the entire state of the application and bring it up successfully somewhere else. We also have to deal with server licensing models. Some of these server licensing systems don't like it when this node disappears and pops up over here, and things like that. So there's things like that. And then also Creo itself was not leaves provisions for handling device drivers, but doesn't really address them. So you have to develop a device driver or plugin or something like that to address it. There's another, I should mention, there's another GPU vendor, AMD, the MI300X, I think it is, or MX300i or something like that. That GPU actually also has Creo integration with a device driver. So before I get into that, let me explain more about how we try to minimize the interruption window for transparent checkpointing. In this example, we developed for EDA, but also applies to the Kubernetes use cases. We first of all initiate that freeze, and so this red area, this is time versus the different parts of the stack, the software, the memory, a local SSD or an ephemeral drive, and then a file system somewhere out there, either on the cloud or on-prem, where you can deposit all these snapshots of the machine state. So we first have to freeze this thing, and that takes a certain number of seconds. And then while we're doing that, we actually go into what we call a copy on write mode, where we can unfreeze it, but any new changes are stored in memory. At the same time, we are also putting the files, local files, taking a snapshot of those and copying the local files in the local memory asynchronously to an external file system where we can bring it back onto another instance. So that's how we're compressing the interruption time. So we can get the checkpoint, transparent checkpointing overhead down to ideally 1% to 2% of the total runtime of an application per checkpoint. So there is some trade point there. If you take checkpoints every hour, and you could actually if you accumulate too many checkpoints, actually, then it becomes uneconomical. But there's some minimum where the right number of checkpoints versus the time to replay the job from that point makes sense. And so our goal is to actually minimize that amount of checkpoint overhead. and that's what we've been working on. And then now I'd like to talk more about Kubernetes. And most people, I see two schools of thoughts. Some people say just run stateless apps on Kubernetes, but we also see a lot of people increasingly trying to run stateful apps on Kubernetes. And some of these are fairly long running, or some of them are on public cloud instances. They want to use public cloud spot instances to save costs. And so that's why we've been working on this for the Kubernetes community. Another, besides spot instances, another major use case is just hot restarting and rebalancing of GPU or CPU workloads, boosting utilization. One of the biggest problems today is GPU utilization. A lot of GPUs are only 25, 30% utilized, just because it's not easy to move workloads around, or they're actually memory bound, or other reasons. And we'll talk more about that and give you some examples. And then also people, as I mentioned, want to save and restore their notebooks. They may want to, if they're a Kubernetes operator, they just want to drain the node or do auto scaling without having people get mad at them for moving their jobs around and having them take longer to run because they have to be restarted. And then also, again, a lot of applications are being brought over to Kubernetes. We're starting to see that now, especially on the HPC side. There's a whole track at KubeCon later on this week where it's just about HPC and batch that are being moved on to Kubernetes, where I think this kind of checkpointing would be beneficial. So what we did was we developed an operator, and then what happens is we have a daemon set in the worker node and a sidecar container inside the pod itself, and then we can dump everything when we checkpoint a particular pod to a persistent volume that's designated by the user to preserve his privacy. And it's a two-step deployment process. We can use first of all, we just install this operator that we've developed, and then you can annotate the manifest for the particular stateful application that you do want to have checkpointed, and that's about it. And so, excuse me. Now I want to talk a little bit about something new. You guys get to be some of the first people in the in the community to hear about this. What we've been doing is Memverge is a inception partner with NVIDIA, and so we've been working on their GPUs on how to checkpoint and restore those. There are other techniques out there already where you basically kind of fence the GPU area and try to capture, basically log all the memory and capture it all while it's running. But this is a more direct implementation where basically NVIDIA in their CUDA driver is starting to implement its own built-in checkpointing capability, not that different than what Creo is doing. And so we're collaborating with NVIDIA to bring that to the community. So there'll actually be a presentation on this tomorrow or this week at GTC up north. And then also I'll be talking about this at KubeCon over in Paris later this week. So what's going on is that the CUDA drivers, the newer CUDA drivers at some point, you won't see it officially in the latest 12.4 CUDA driver, but in the not too distant future, you will see CUDA drivers that have capabilities to checkpoint. And what happens is that the CUDA driver itself will implement its own checkpointing of the GPU area, and basically dump all of its memory and state into a host system memory, and then you can either resume operations or you can just kill the process, and then restore is the reverse. So it's very similar in many ways to Creo, except it's built into the CUDA driver architecture. And so we've been working with this on a POC level with NVIDIA to capture that state. So what happens is now we have a two-stage problem. We have to first of all freeze the GPU, and then copy that into system memory, and then freeze the rest of the CPU along after that. Well, sorry, I take that back. We freeze the GPU first, then we freeze the CPU, and we're putting all that into a checkpoint image along with any file and object storage state. So it's a two-stage operation: freeze the GPU first, then freeze the CPU processes that are associated with that GPU, and then put everything into a checkpoint image. So this illustrates that checkpointing, and this reverse illustrates the restoration of that. So we have to first of all take the checkpoint image, which is stored on a file system somewhere, and then recover the GPU state first, and then bring up the CPU and release the whole application. So now I'd like to just show you a quick demo of this. Again, this is one of the first times we've ever previewed this demo. And what we're going to do is we built a Kubernetes, actually it's a GPU and CPU snapshot operator that will drain a node and then migrate it to the schedule will automatically migrate it to another node. So let me run that. And I apologize, this is a little bit of an eye chart. But basically, first thing going on down here is we're just discovering displaying the nodes. There's two workers there. This is a T4 GPU on Amazon. Then we're launching up in the upper corner there, we're launching the operator, and this case we're running a TensorFlow MNIST demonstration GPU training load. And then on this upper right, you can see the container being started up on the particular worker. And again, I apologize for the size of the font here, but I have some good news for you if you want to look at this again later on. Then we turn on the logging so you can see what's going on. So basically the TensorFlow application is being launched and compiled and all that good stuff. And then down here, the epic, what we're doing is watching all the training epics go by. And while that's going on, the epics are counting upward, so it's up to epic 7 or so. We're issuing a node drain command down below in this console as if we're going to take it down for maintenance. And then over here, you can see it terminating in the upper right corner of that node, and then it'll restart the other worker with that same workload. That's where it's going here. Container's being recreated. And then down below here, the key thing is you'll see this thing resume. Right now it's at epic 7. Normally, if you restarted this thing, it would have to go all the way back to the beginning of the whole training cycle and go from there. But here, we're actually seeing this resume from where it left off. Let's see here. Yeah, there it goes. Now it says running. And there you can see it starting to advance again. So basically that's the end of the demo. I just wanted to show you that this is possible now to be able to stop a training workload on Kubernetes, do what we call a hot migration to another node, and restart that pod and pick up where it left off. Okay, so let me move on. So yeah, again, that was an eye chart. So what we did is I recorded a bunch of demos, and if you click on that square, you can view them at your leisure. But we just show an example of a TensorFlow on a bare metal checkpoint restore. Here we're also running more like an HPC workload. So NVIDIA has something called Parabricks. If anybody's from the computational biology side, there's this secondary analytics that goes on when you're doing DNA sequencing. We're trying to line up the sequences with a reference, and Parabricks now has been put on GPUs, and we can demonstrate that running in a checkpoint restore fashion. Then we have our own opinionated version of checkpointing and restore called Memory Machine Cloud, and where we do a migration of Parabricks from one instance to another, a spot instance, and that has to be done within a For Amazon, you only have 120 seconds from the preemption signal to when the node gets terminated, so we have to do everything pretty fast. And sometimes these nodes get pretty big. And then the last one is a TensorFlow example on Kubernetes I just showed you, so you can look at that again if you want to see that. So those are demos. And so what's ahead? Right now, we're working with NVIDIA to complete some modifications to their CUDA driver. It's about to go into preview mode. So if you're interested, you can email me. I can let you know exactly when it goes into preview mode from NVIDIA. And then also we are working to with NVIDIA. We're going to coordinate and contribute and upstream some changes we had to make to Creo to accommodate this implementation of checkpointing. The reason being that, again, this is a two-stage phenomena here. We have to keep the GPU process IDs alive long enough to checkpoint those first, and then shut them down along with the rest of the application. So there's some modifications that have to be made, and then we'll be working on production-grade applications and operators. But my call out to you guys is, what use cases do you see for transparent CPU or GPU checkpointing? Well, I kind of gave you some ideas of what we're thinking about, but we're always looking for people to collaborate with on this. And so I mentioned earlier we have an opinionated version of checkpointing and restore for batch operations on clouds like Amazon, and it's called our memory machine cloud. And this is a way that we can combine not only migration based on using spot instances, but we also can combine that with our own kind of auto scaling or vertical resizing. And this again is for batch operations. It's outside of, it's more for the HPC community. But this gives you an example. So again, I'm going to use a computational biology example. This is the kind of the CPU and memory profile as a function of time for a metagenomics workload. And you can see it goes up to a couple thousand seconds in time. And by just turning on, if you just use an on-demand instance on Amazon to run this workload, the time, it costs $9.10. Now, if you turn on what we call WaveWriter, and WaveWriter is a capability that allows us to detect whether there's too much memory or not enough memory. So here you can see at the beginning of this workload, there's a lot of memory here being used. It drops off, and we automatically checkpoint this thing and resize the instance down, and then bump it up slightly here. So there's actually three different stages here where we're migrating this thing automatically, or what we call wave writing it based on the size of the memory, or in some cases also on the size of the CPU utilization levels. We can automatically migrate. So if we automatically migrate with on-demand, we can cut the costs by about 17%. Then if we just use spot instances alone without wave writing, we can cut the cost by about 67%. And then if we use spot instances plus wave writing, now we can get down to a 75% reduction in compute costs. So just give you an example of ways to use checkpointing in your own data centers. Now I'm going to pivot to the second topic of the day, which is Computer Express Link. How many people have heard of CXL? Anybody raise their hands? Nobody? Okay, I'm not surprised. It's relatively new technology. It's emerging, and let me explain the motivations for it. There's three motivations. One is, the biggest one is what we call the AI memory wall. There's just an insatiable appetite of AI to have more and more, especially high bandwidth memory. And this is not only for training, but this is also increasingly for the inferencing side of the workflow. So the training side here, we're just showing how fast the number of, how many billions or trillions of parameters are being used. And those have to be stored somewhere, they have to be retrieved quickly, et cetera, et cetera. And there's only so much of this that can be contained in the HBM memory of GPUs before they start melting, literally. There's issues like that. And then, so that's one problem. But also, the other problem that's out there is for cloud operators. A lot of times they're allocating by workloads and packing them into virtual machines or pods or whatever by CPU core, driven primarily by CPU core requirements. But that also can cause a lot of memory just to be underutilized or stranded. And so Microsoft estimated that up to 30% of the memory in their servers is stranded or just allocated but not used, things like that. So there's that kind of issue. So one is a shortage of memory, this first one. This one is actually underutilized memory because it's trapped in a local node and it cannot easily be reallocated elsewhere. And this third one is just a general problem with systems that the core count is going up and the memory bandwidth is not keeping up with it. So the CXL consortium, which stands for the Computer Express Link, formed several years ago, and it basically includes 255 members. Basically, as you can see here, the entire hardware industry has joined this consortium to help solve this particular memory bound or memory wall problem that the industry is facing, and I think it's going to be increasingly more challenging in the AI world. And they have developed a specification starting in 2019 of something called CXL 1.0, and then 1.1, 2.0, 3.0. Basically, this specification today is at this 3.1 level, and that pretty much maps out the next several years of how CXL will be rolled out. And what I'll do now is I'll show you what that rollout looks like. First of all, the thing I want to let you know is that memory today, DRAM memory today runs on a DDR bus, and it's a parallel bus. It takes up a lot of space in your system, and the whole idea of CXL and just the physics of it, and it does not lend itself to scaling more memory because of this parallel bus. So people are starting to use the serial protocol, and the standard now in the x86 world is PCIe, and it scales by number of lanes, so it's a serial process. And today, the industry is shipping at PCIe Gen 5 right now, and so this is the roadmap of how the PCIe generations, as well as the number of lanes, so the number of lanes, like a number of lanes on a freeway, can scale up. So you can see here, when PCIe Gen 7 comes out in about 2 years, we'll be up to about 512 gigabytes a second here with 16 lanes of PCIe. So this is a better way to scale coherent memory. And then the CXL use cases, and I'm just borrowing these slides from the CXL consortium. And there are three types of use cases that are being addressed by CXL. The first one is what they call a type 1 device, a caching device, or accelerator. So the classic would be a NIC card that where we can you can load or read directly from the cache in the NIC card and transfer things faster that way. And it's done in a coherent fashion. So all this is being done in a memory cache coherent fashion. Second one is type 2, and this is intended for accelerators and GPUs, where they can trade off sharing this memory and who has the rights to that memory. And then this CXL type 3 is for memory expansion, where you can add more memory now on the PCIe bus to expand the memory. So a lot of systems like, I think the new AMD systems, they may only have one DIMM per channel or something like that, one DIMM slot per channel. And so one way to expand those is to use these CXL memory expansion approaches. And then when it gets to type CXL 3.0, so 3.0 is where it gets really interesting, because now we'll be able to create disaggregated memory pools and then also allow memory sharing of that memory pool among multiple hosts. And that's also not too far around the corner. The industry is already demonstrating prototypes of this this year. And what we're showing here is a CXL switch, a PCIe-based switch that supports the CXL protocol, and multiple hosts up here that are accessing these memory devices down below. And these memory devices can be partitioned into what we call MLDs, multiple logical devices. So for example, each one of these could be a 256 or 512 gigabyte memory card built by your favorite memory supplier, Samsung's, SK Hynix, or Micron, and then you can take, I believe, like 2 gigabyte slices of this thing and allocate them to different hosts. So all sorts of interesting use cases can come out of this. And then also there are cases where you can actually share that same memory address space between 2 hosts, which is something that we're looking at also. So this is a little bit of a detail, but it just summarizes those specs, the progression of the specs, and the increasing number of capabilities. So the initial CXL 1.1 spec established in 2019, those products are just starting to ship in the second half of this year. And those will just basically allow you to expand memory in existing computer servers, either Intel or AMD, Genoa, and some flavors of ARM processors, and basically allow you to create a fat memory node. So some workloads like more memory, people are running graphs or some other kind of analytics. May be better to have more memory and fewer partitions or whatever. And then CXL 2.0 also is being previewed along with 3.0, which will allow you to do, first of all, pooling, and then at least at a single switch layer. And then CXL 3.0 and 3.1 will allow multi-tier switching, kind of like you would see in a regular fabric architecture, multi-layer switching to allow even bigger pools to be created. At the same time, there's also new memory technologies coming out, like memory semantic SSDs, which will give us a lower cost type of device, but that also speaks in memory semantics load store fashion. And I think that's going to be important as we go forward with AI and ML workloads. This is more of an idea of the software stack. And so our company's been busy contributing to the Linux Linux kernel to enable CXL capability. So right now, this is a timeline. So from left to right is what we have today down below, and then future additions to the kernel to enable CXL capabilities. And then up here, we're showing the user space and the standard MEMAP and malloc kinds of capabilities. So first of all, the first way CXL can be used is as a DAX device, and then there are already hardware vendors that can interleave so you may have some of your memory sticks in a DIMM slot and other memory now inserted into PCIe, and we can basically interleave across those, or kind of like stripe if you're used to RAID technology, between all those memories and get higher overall bandwidth. So that's one capability that's actually being built into some hardware or capabilities. And then the second approach to consuming CXL today is to have it presented as a zero CPU NUMA node. So basically, that memory now looks like a one NUMA hop away kind of memory, and use auto NUMA or something like that to utilize that memory in the application. And in some cases, companies like ourselves, we're building memory tiering software where we can more intelligently place the memory pages, either to make them basically NUMA aware. So we can move pages that are hotter to the closest point to the compute itself. So we may be doing hot and cold page demotion. There also is capabilities that also been contributed to the Linux kernel called TPP, transparent page placement. Most of that work was done by Meta. That will also help you automatically move pages around, hot and cold pages around in a CXL context. And there will be further extensions to this to allow for shared memory. And then right now there's a hardware level interleaving, but Membridge also is contributing to the Linux kernel, a kernel-based interleaving. So now we can do weighted interleaving. So you may have, for example, 80% of your memory is in DRAM and only 20% of it's on the CXL. Well, we need to weight it accordingly. You know, how that interleave is done, not just, you know, mindlessly just use up all the memory in some sort of striping fashion at the hardware level. So things like that, and then also making sure that certain things like the kernel functions themselves don't get subject to being moved to remote memory areas and things like that. So anyway, there's a whole roadmap of this, but there's already enablement today of CXL going on, and this is some just to make this more tangible. Some server vendors are starting to ship CXL-enabled servers, and there's two ways to install memory. One is to use these memory modules that look just like NVMe disk modules and plug into a similar slot, but it does not need to be CXL-enabled. It's called an E3.S, and those come in fixed capacities. From this example, Samsung has 128, 256, and 512 gigabyte expansion modules. And then another approach is to put an add-in card. This add-in card here can actually hold 2 terabytes, 8 sticks of 256, 2 terabytes of memory, and would take up 2 PCIe slots. So this is how you would create what I call a fat node, one that has a lot more memory than you would normally have. So there are certain workloads where I've seen, you know, 40 plus gigabytes per core needed to run those workflows effectively. And this gives you some examples. In the HPC database area, we can get faster time to result by these fatter nodes and higher performance ratios. And then by using memory tiering software, either our software or stuff built into the kernel, we can consolidate nodes. So in one case, we had a situation where 100 nodes with 64 gigabytes a piece of memory that took 2 weeks to run, had lots of failures, kills, data skew problem, whatever. We consolidated into one single 4 terabyte node and took 4 days to run. So from an economic standpoint, you could start with a baseline of a single node of 64 gigs. If you want, you could scale it out. So everything, basically the queries per second would double, but then also your server costs would double. Or the other alternative is you can, in some cases, double the queries per second, but just by adding more memory. So some of this is a little bit like, years ago I remember Fusion IO came out with a technology where they added basically local cached NVMe memory to a node, and they could consolidate or increase CPU utilization. In that case, they were reducing Oracle licenses and things like that required. Similar phenomenon can happen here with memory expansion. And there's 2 ways that we can tier or place memory more intelligently that we've been working on. One is what I mentioned earlier, hot and cold pages of memory, and promoting or demoting memory, and using various profiling hardware or other types of profiling techniques to detect when we should move pages around. And then the second one is to do bandwidth optimized memory placement. So some applications are capacity bound, memory capacity bound. Some we find are memory latency bound, and other applications are memory bandwidth bound. So figuring that out is part of is a key thing. And so for the bandwidth bound memory applications, there are various strategies of weighting the interleave between the memory in the system DDR bus versus the memory on the CXL, so we're still experimenting with some of that stuff, but there already is some very promising results. So, as a matter of fact, at GTC later on this week, the NVIDIA conference will be showing this demonstration at the in the Micron booth. And this is a batch inferencing operation. It's using a 66 billion parameter model, and this is the batch size and prompt length, 512. Basically, what we're doing is we're comparing system memory plus, this is a batch inferencing problem. So we're comparing system memory plus NVMe versus system memory plus CXL, RAM memory. And what we find is that we can cut the total wall clock time. So what you're seeing down on this bottom axis is time in seconds. And then on this axis is GPU utilization. So the bottom line is that, and this blue line here represents the CXL memory offload versus using standard NVMe disk offload. And so basically what we're seeing here is that we've cut the total batch time execution in half, and we have doubled the GPU utilization, so it's running at about 90% instead of, more like about 35, 40%. So it's a win on both sides there, basically. Faster time to insight and better utilization of GPUs. And GPUs are very hard to find. So this could be an approach to for people that do batch inferencing to speed up their throughput and performance. And then on the pooling side, that also is in a prototype stage. So there are people out there building these CXL switches that will allow multiple servers. I'm just showing two here, but connect to let's call it a memory appliance or a JBOM, just a bunch of memory, and allow them to either share it or at least allocate from a pool to give you a more what we call composable infrastructure. So you can have a composably, dynamically allocate this memory to different use cases. And one example of this will be in the Kubernetes area, where you can imagine instead of having to just be killed or whatever, or having just auto-scale migrating nodes from one node to another bigger node, you can imagine another type of pooling where we allocate, instead of the action being kill this thing and move it somewhere else, is give it a squirt of memory. And so it overcomes whatever the skewing, the transient skewing or out of memory problem is. So this is something else that we're working on. So I don't want to go through all this as detailed, but this is being done also in conjunction with the Open Compute project, which I'll talk more about in just a second. And then here's another example. We've been working with AnyScale on how to the AnyScale architecture is interesting because it's one of the first that has a distributed shared memory object data plane as part of its architecture. And what we think we can do is possibly accelerate that performance of that by not having it distributed, but actually shared. It's among all the array nodes. So we are prototyping a project called Gizmo that allows you to share those memory objects. And what that does is reduce the number of memory copies and also probably gets rid of a lot of communication overhead because of the network's traffic to move this data around. And I think this will be significant because when we look at especially on the inferencing side, we expect things like key value caches and things like RAG, retrieval augmented generation, are going to require huge amounts of in-memory, memory-based semantics and memory-based architectures to support those kind of AI workloads. They don't work very well with block or file access type of modalities. They need that granularity. So just to wrap up, if you guys are interested, anybody's really hardcore interested, there's something called the Open Compute project, sponsored by Meta and other players in the industry. And within that Open Compute project, which is just designing general data center scale stuff, there is a subgroup working on CXL-enabled systems. That's called the Composable Memory System Group. And so if you're interested in participating, this is one way to get involved in that community. So I'll just leave that up there. And with that, I'll wrap up and answer any questions. Thank you. Yes.
In the explanation, was it Creo that you did the check for checkpointing?
Right.
So it looked like the way that works is it's running on the Linux system that you're checkpointing, and it's modifying code or in memory, and then when you go to the next diagram where you're actually checkpointing a container, is that or I guess was it even a pod?
Yeah, we could checkpoint a pod.
Yeah. Is this running inside all of the different instances or all the different nodes in that pod, or is it the way around?
Only on the nodes that you designated. So if you designate this as a stateful pod, we'll inject a sidecar in there and checkpoint that only. Yeah.
But you can't. It looks like you said you could do it recursively down a process tree.
Yeah, that's Creo itself.
Yeah, but you can't start from systemd or init, right? Because then that will include the process that's actually doing the checkpointing, and it'll freeze itself, right?
Yeah. I think.
So how do you actually checkpoint the whole container?
Well, yeah, this may be above my pay grade, but I think there's situations where you have an init and then the actual running container, and so I think we have a way to.
Well, right. I mean, I don't know if there's an init per container, but per node anyway, right?
Yeah, within a pod, sometimes there's multiple containers, and one sometimes is just used to init the thing, and then the other one is the actual executing thing.
So all the processes for a given pod are in a subtree, you think?
Yeah, yeah. So the ones that are running over here, not the init, we'll checkpoint and bring up elsewhere. Yeah. Okay. Any other questions?
So just as a data point, I until recently worked for a large quant hedge fund, and they use Creo checkpointing like this to run lots and lots of simulations on spot instances on the whole cloud.
Yeah.
So similar kind of thing.
Yeah.
In your product where you're sort of adjusting the memory for an application.
Yeah, wave writing it, we call it, yeah.
Wave writing. I obviously can understand how you sort of deal with like memory decreasing, but do you have instances where memory jumps suddenly and you can't catch that before the app crashes?
Yeah, we can set thresholds before it reaches some point, and then before it ooms or whatever happens to it. So we have to set a threshold, and that's part of our policy. And there is some heuristics involved. We could run this thing, and we kind of learn the behavior of this thing over time and go that way, yeah. All right, good questions.
Any other questions?
With these CXL memory switches, I assume that technology-wise they're probably not terribly different from a modern like Ethernet switch.
Yeah, there are PCIe switches out there already.
Okay.
And now these PCIe switches are being augmented by the CXL protocol. And so quite honestly, one of the challenges will be extending the coherency domain to a much larger area. And so I think that'll be rolled out gradually. Initially, what we're showing here with this shared memory object, for example, is really more for analytics or ML, AI ML training, where it's kind of a write once object, immutable object kind of model. But we're also finding use cases for this kind of initial implementation of CXL in the pub sub area for, among other things, high frequency trading, market tick data, things like that. So there's some interesting use cases starting to pop up now. Yeah. Okay. Any other questions? If not, I am going to boogie out here and run to KubeCon. So thank you very much. Appreciate it.
Thank you.